Okay. All right. So first thing first, we're gonna do a few things today. The first one is to go over question number 7 because I forgot. I ran out of time to cover it last time, but nobody reminded me to go over it. Over the recording when I got home. So we'll go over it now. And I think that's exam 1 from this one. It's the exam 1 of the previous semester. And it's the last question. The other mic is not working because it ran out of battery. Question number, oh no, it's not 7, it's question number 6. All right, so question number 6 was the question that I did not go over last time, and so we're gonna go over it quickly now. All right, so we'll just read the question first. What is the closed form, which means it doesn't use sigma or use dot dot dot, it is just a particular expression of this? You may assume A is less than or equal to B. A is a natural number and B is a natural number. Okay, so that's the first part. Derive your answer step by step. Your answer may use any basic arithmetic operators like multiplication, division, addition, subtraction, but it may not include summation or undetermined addition of terms like the dot dot dot. So I want you to give me a closed form, expression of the value of the double sigma thing. Okay, so now the question is, how do we deal with the double sigma thing? First thing is, what is sigma? Okay, sigma is the summation, and the indexes tell you what we're summing over. So when you look at just the inner sigma, which is the sigma of I equals to 0 to j, and then it's a constant of 1 that we are summing over, what does that mean? We are setting up a loop for I equals 0, I is less than or equal to j, plus I. That is the setup of the loop itself. What are we doing in the loop? Some kind of summation term gets incremented because it's adding 1 each time per iteration to the sum term. Okay, so what do we get? What do we get from the inside sigma? Yep, we get j plus 1. Because the number of iterations that we are going to go through is not j times, it's j plus 1 times. Because the first iteration is when j equals to 0. The last iteration is when I equals to j. It's only when I is greater than j that we exit that loop. So that's why the inner sigma is really j plus 1. Okay, so let me just write it down on the tablet, so this way we can actually look at it and get it recorded. Okay, so we'll start up. Oh, okay. Of course, it won't work because I haven't plugged it in yet. There we go. All right. So the first thing I'm going to do, which is something that you cannot see, is I'm just going to copy it from the question to the tablet, so that way I can work on the tablet after that. So we have a sigma j equals to 0 to b, and then in parentheses we have sigma I equals to 0 to j, a constant of 1, and close paren. There we go. All right, so we want to derive this. So the first thing we know is it becomes the sigma of j equals to 0 to b, and then the inside sigma becomes j plus 1. Okay, so first of all, is this part okay? Because if we have any questions about how we got from here to here, how we turn the inside sigma into just j plus 1, then we need to talk about that first. Yep.
Does j start as 0 or a?
Is that a? Oh, okay. So we'll turn it into a. Eraser. Okay. I probably just didn't read my question carefully, so it's a and a here. There we go. All right. So is that okay? But do we have any questions about how the inner sigma turns into just j plus 1? Because we're adding 1 j plus 1 times. If you add 1 j plus 1 times, what do you get? You get j plus 1. Okay? Any questions about that one? Now, if you have any questions about this, the best way to look at it is to give j a concrete value, 2. Okay? So you have a sigma I equals 0 to 2, 1. What does that mean? You have 1 plus 1 plus 1. The first one is when I equals to 0. The second one is when I equals 1. And the last one is when I equals to 2. You add it, all three, becomes 3, right? But how does 3 relate to j? Or 2 in this specific case? It's whatever the count plus 1. So that's why we kind of know that the inner sigma turns into j plus 1. So you look at this and go like, okay, now what do we do with this? So now we have sigma j equals a to b, and you can break it up. Okay, one side deals with j, and then the other side j deals with the constant. Oops, back. Okay, would that work? Well, because the original thing that we are summing has 2 terms and they're added, this only works when it is added, okay? But when it's added, then you can, because of the commutative property of addition, we can move things around. So we keep all the j's to one side and then we keep all the constants ones to the other side. So we can break a sigma into 2 sigmas and they have the same indexes. Is that okay? All right? So the constant side is the easier side to deal with because it becomes b minus a, because that's the number of plus 1, because that's the number of times the loop is going to go through. The other side looks a little bit cumbersome, okay? So we have to somehow convert it into a form that we recognize. So the one that we recognize is when the index starts from 0 and it ends at a particular number, right? Right now it starts at a, which is not something that we can quickly recognize. Yes? Yep. Exactly. So we will turn this into sigma of j equals a minus b, b minus b, and then in the term that we are summing, we adjust and say it's j plus b. Is that okay? So I'm changing the index so that the indexes or the ends of the index, they are now b less than what they used to be. But to make up for the index, which is used inside the summation term, to adjust for the index changing, I'm adding b to each term that I am summing over. So it has the same effect as the original summation term, except I'm translating everything. Is that working or not? Yep.
When you have j start at 0, so we'd have j equals a minus a.
Right, okay, yep. You're right. We wanted to start with 0 and not end with 0. Thank you. Although if your loop can work with decreasing the index, this will work too, except it's kind of backwards. Okay, so we'll work with it in the way that works better. Okay, so we'll get rid of this, get rid of this, get rid of this, and just use a. So we have a minus a, b minus a, and then plus a inside those terms. This is just to enforce the start index is less than or equal to the end index. If I do not have that rule and the loop can decrement the index, then it will still work out the same way. Is that okay? All right. So then we use the same trick and we break it apart. So we now say this is sigma j equals to 0 to b minus a. The first sigma is just summing all over the j's. The second one is summing over a constant because it's 0 to b minus a, but the term that we are summing over is just a itself. And then the last term, we still have the same last term. We'll keep it around like that. So are we okay with this transition? I'm just breaking apart a sigma that has a summation term that is by itself a sum into two different sigmas. Same indexes, okay, same everything, except j goes into one its own sigma, and then a as a constant goes into its own sigma. Is that okay? Yep.
Couldn't we have, so in the second step where we split the j plus 1,
Mm-hmm.
so you did a trick kind of where you said we add 1 b minus a times,
Mm-hmm.
and then just add our position. Couldn't we have done the same with the j? We add j b minus a times plus the j at our position. So just the sum from j equals a to b, wouldn't that just be j times b minus a plus j?
Yes, we can do that. I'm just doing it very, very step by step. But you could, yeah, you could translate this into, you know, turn this one into, change this one into the index. So you adjust the index to make this term looks just like a j, but you have to make sure that this starts from a 0, and then plus some summation of constants. So we could have adjusted everything from that point, but I'm just doing it one step at a time. All right, so what do we get now? The first one, I think we recognize it, don't we? Because when we try to figure out j equals to 0 to n, and then j here, we have seen that before. When we had to deal with the g function, when we talked about aleph null, we have seen that. So the first one really boils down to whatever the index is, b minus a, times b minus a plus 1, and then the whole thing divided by 2. What about the second one? The second one is actually kind of interesting because a is a constant. A does not depend on j. A is just a number fixed from the very beginning. So it can use the same trick that we have in here because a and 1 are both constants. This time we are adding b minus a plus 1 many times the constant of a. What do we get? A times b minus a plus 1, the whole thing. So we just say this is b minus a plus 1 times a, okay? And then the last one is just copying from the top, which is just b minus a plus 1. And if you leave me with just this equation, I will count it as 100% correct. In other words, there's no need to factor and simplify and do all that stuff because all I asked was a closed form, and this is a closed form. It can be simplified a little bit better because you can see how b minus a plus 1 is common to all three terms. So you can factor it and do all kinds of stuff to make it look cleaner, but it's not necessary. Yep.
Where did you get the
Number
number 2?
2.
Like with the first part, it's b minus a times b minus a plus 1 over 2.
You mean this part here?
The bottom part, where did you get the denominator?
The 2?
Yeah.
That came from, okay, so let me see if I can find the notes for that.
Oh, it's 4.
Yeah, it's something that we derived in class. It's in the aleph null notes. And I'm just looking through. There, okay, right here. Yep, it's right here. So let me zoom out just one level so that we can see the derivation. There we go. So it's coming from here, which if you ignore the first line and all the lines in between and only focus on the last line, so the sigma of I equals to 0 to x I is I times I plus 1, the whole thing divided by 2. So you can kind of skip the proof part and utilize the established equality. Now, when you're studying, I do not recommend ignoring the steps in between. Even though you may not need to prove anything like this, it would still be handy to understand the mechanism of how we connect one step to the next. Okay? And also keep in mind this is not the only way to prove it. There are many other ways to prove this particular equality. One way is proof by induction, okay? But we are not going to use, this is strictly just using algebra to prove the same thing. Yep.
Can you pull up the notes again?
The,
Just yeah, that's sufficient.
from the question or from my
You
tablet?
yeah, the tablet.
Okay.
So the 0 to b minus a of a,
Mm-hmm.
where did that go?
That became this term because I'm adding a, which is a constant, b minus a plus 1 times. So that's why it becomes just a times the number of times we're adding it.
Oh, so did the I must have missed it. Did the question say to get the answer strictly in A and B?
It said turn in a closed form expression.
Would it have still been closed form if you found an expression in J?
Say that one more time.
Would it still have been closed form if you found an expression in J?
If you still have a sigma, it is not closed.
No sigma, just A, B, and J.
Why would j be there?
From the summation from
Mhm.
J equals A to B of J plus 1, is that not equal to B times J plus B minus A times J plus 1?
But j is an index. It changes all the time.
Oh yeah, that's right.
J is the variable that keeps changing in the loop. Yep. So you cannot have j in the closed form, or generally speaking, j should not be in the closed form. Yep. So is that okay? I mean, that kind of explains the last question. Yep.
The second equation where the b minus a and the a sum of a, why is a constant? Why isn't it similar to j?
Because in the original question, it looks like this, right? So a is the lower bound of j and b is the upper bound of j. They become the boundary of a loop. And then j starts with the value of a, it ends with the value of b. So they're constants. You do not change a or b during the calculation. You change j starts with a, then becomes a plus 1, then becomes a plus 2, until it becomes b. Okay? Now, if this is, if it's looking too abstract, the best way to look at something like this is to give it concrete values. Okay, so we'll just say, okay, for sigma I equals 0 to 3. Okay, what does it mean? Well, okay, so we have to specify what we are adding over. So let's not make this I, let's make it 1. Okay, which is a constant. So what this means is I'm adding 1 plus 1 plus 1 plus 1. The first one is when I equals to 0, when I equals 1, I equals 2, and I equals 3. Is that okay? So I'll give you one more thing, one more tool. If I give you a very general, okay, I goes from A to B, and this time I don't even tell you what we are summing over, except I say that this is a function of I, okay? This is as general as it gets, right? So what is this calculating? So I turn this into a loop. I say for I equals to A, I is less than or equal to B, plus I. This is a poorly rendered semicolon. Okay, so we also want to initialize a sum to be 0 to begin with. So we zero a sum at the beginning. And then inside the loop, the only thing we are doing is sum plus equal to f of I. That's basically, so this is the equivalent to what that is doing. Well, I mean, you have to basically say result or sum is the value of this. Is that okay? I'm trying to turn an more or less abstract mathematical symbol into something that is kind of like C code that you're familiar with. Is that okay? kind of the same way that I do with the for all and there exists, that sort of thing, is to turn an abstract math concept into something that's actually iterative, something that you can actually run. Is that okay? But how does this handle the case when we are summing over 1? I can define this, can't I? Right? So that's why f of I covers, when it is a constant term that you're summing over, or a term that does not depend on I itself. Which also makes that function non-injective, but not necessarily surjective or non-surjective. Because if I don't tell you about what is the set of the codomain, you can't really say whether it is surjective or not. Because if I say the codomain is a set of 1 as the only element, then it is still surjective. So you have to be careful with surjectiveness. What is inside the codomain? Sorry, I jumped around the topics, but I looked at this and go like, I can use it to explain, surjectiveness and why you have to be careful about the size or the actual membership of the codomain. But that's my brain kind of jumping. So is that okay? We good? All right. All right, so if this is okay, then the next thing we do is to talk about the homework that was due 25 minutes ago. Okay? So we'll look at the homework assignment. I said it would look really bad. As it turns out, it's not quite as bad as I thought it would be. Okay, so this is your CNF homework assignment. All right, so I'm just going to copy the question to the tablet, and then we'll use the tablet to explain it. Okay, so the negation of P or Q, the whole thing implies R, or negation of Q and S or not T. There we go. Okay. So I think I got it right. Okay, the negation of P or Q, the whole thing implies R, or the negation of Q and S or not T. Is that right? Sounds about right. Okay. So the first thing we do is we get rid of the implication. So on the side, I'm going to write here what I'm using to perform that step. So on the side, I'm just going to say A implies B is really the same thing as not A or B. Okay, so that's the rule I'm using here. So there's still a big negation on the outside. Then we have the negation of P or Q or R. And then on the other side, we can apply the De Morgan's law. So De Morgan's law, okay, so now we also want to say what is De Morgan's law. The negation of A and B is the same thing as not A, the whole thing, or not B, the whole thing. So by using that, we can now say that this is not Q, or the negation of S and not T. So are we doing okay so far with this? The definition of implication is for the left-hand side of the overall disjunction, and then the De Morgan's law is for the right-hand side of the disjunction. Go ahead, and then you. Yep. As yep. We are not changing that yet. Thank you. Let's do it. Or because we haven't done that yet. Okay. Any questions? Okay. So we look at this and go like, what do we absolutely have to do? Well, we cannot allow negations on the outside. Okay, we cannot negate some kind of expression. So if you're negating some kind of expression, whether it's conjunction or disjunction, we got to take care of that. In other words, one of the main objective of the transformation is to move the negation all the way into just variables. That's one of the things that we absolutely have to do. So the next thing we do is to apply that part of the De Morgan's law. It's a slightly different De Morgan's law. It says the negation of A or B is the same thing as not A and not B. This is the other De Morgan's law. So now we can apply that to this overall negation here. So now we have the negation of P or Q and the negation of R. Now it's very important to keep the level of parentheses so that we can maintain, we know what we are doing, okay? So that becomes the entire left-hand side. And then the right-hand side, let me see what we can do with this. Well, we can still apply De Morgan's law because we do not like a negation applied to a conjunction or disjunction. So you don't have a choice, okay? When you see that you have a negation on the outside and an operator in the inside, you have to use De Morgan's law to move, quote unquote, move the negation to the inside, okay? So we'll do that part. Not Q is the same, and then we keep this OR, and then we apply De Morgan's law here. So this becomes not S and not T, okay? So we are still using De Morgan's law on the right-hand side. So on this side, we'll go ahead and simplify a little bit. So this is not a very important derivation. All we are doing is to get rid of the double negations. Okay. Okay, just get rid of double negation. But if you do want to know what type of rule we are using, we're simply using that. Okay. All right. So at this point, we have something that goes like, it looks like, we are pretty close, but we're actually not that close because we have this, you can dissolve this parentheses if you want to, but we are not going to do that, okay? So instead what we're going to do is we're going to distribute the Q or over the not S and T. So we will use distribution. There are other ways to do this too, but this is the way that I choose to do it. So we're going to use distribution this time. And the distribution rule that we are using is distributing an and over or. So that means, A or B and C is the same thing as A or B, the whole thing, and A or C, the whole thing. Okay? How do we know this is going to work? The truth table, okay, is fairly useful, as a proof technique. Okay, so we're going to distribute that. So we end up with not Q or not S, that's one thing, and not Q or T as the other thing. Is that okay? That's just the distribution. So at this point, I have everything in the right place. Because, when you look at distribution, what if A is, okay, if you just look at this distribution term here, you can see how if A is already in the form that we want, A or B is also going to be in the form that we want. If A is a big disjunction of individual variables and negation of variables, so are B and C, the result is already in C and F. Yep. Distribute the left side? The left side does not need to be distributed, and I'll explain why. Okay? All right. So knowing that this is distribution, what if we have something like this? Okay, so on the side here, so I'm going to draw a line. So on the side, I'm going to say, what if we have A and B, or undo. Okay, and C and D. Okay, so what if we start with something like that? Well, it looks pretty close to the one that we have earlier. So we'll treat A and B as if it is just one single term, okay, initially. Okay, so that becomes A and B, the whole thing, or C, and A and B again, or D, the whole thing. Does that work? Based on, A or B and C can be distributed to become A or B and A or C. I'm just treating A and B as one single thing, as one, individual thing. And then we are just dealing with the distribution over C and D. Would that work? Yes? Maybe? Okay. Okay, if that works, then we look at each one and go like, oh, but we can also distribute these, right? So when we distribute those things, we end up with A or C and B or C here. And, okay, with the right-hand side of the overall end, we have A or D and B or D. Would that work? I'm just taking A and B, the whole thing, or C, and then do a distribution. I look at A and B, the whole thing, or D, and do another distribution. Is that working? Is that okay? But why is it relevant? If A is a disjunction of some variables or negation of variables, and so are B, C, and D, then we end up with a a conjunctive normal form already. Is that making any sense? And guess what we have now with our derivation? This is our A. Our A is P or Q. It is a disjunction of variables or the negation of variables. What about B? B is not R, which is by itself, a disjunction. Or we can treat it as if it's just a disjunction, okay? What about our C? Our C is not Q or not S. What about our D? Our D is not Q or T. In other words, we have set it up so that we have our A, B, C, D in exactly this format. And by applying the cross product thing, okay, or distribution, we'll end up with something that's kind of big and nasty, but it is in CNF already. Is that okay? So we'll go ahead and do all these steps. Okay, it's going to look pretty ugly. So we'll end up with P or Q. So we're going to distribute P or Q to not Q or not S. Or not Q or not S. Okay, that's the first one. The second one, so I'm dealing with the second one, which is B versus C. So our B is just not R. So we have not R or not Q or not S. And then we move on to AD, okay? Nope, that's AD. So that would be P or Q, or D is this term over here. So that would be not Q or T. Put a big parentheses around the whole thing. And then we have the last one, which is not R or D, which is not Q or T. Whew. Okay, yep.
All the ors on the right are supposed to
Oh yeah, those are all ands. Sorry. I got all the ands here, and then when I work on the here, I turn those into ors. Erase all that. Turn those into ands, because that's the whole point, right? We want to end up with a conjunctive normal form. Okay. So if you give me something like this, I cannot take any points off, because the homework only said that you are supposed to give me a CNF that works, that is based on the original expression. And this is equivalent to the original expression. I cannot take a single point off if you give me this answer. But some of you may notice, but we can simplify this a little bit. I mean, that looks pretty ugly to me. So the way you simplify it is to say, because it's all disjunction inside each term, so what we can do is to say, oh, look at this guy. It has got a Q and a not Q, and because of the or in between, the whole expression becomes true. In other words, you combine these whole thing and it becomes true, and this row has exactly the same deal going on. This becomes just 1. Anytime you have a disjunction and one of the terms that you are oring is true, the whole thing becomes true, right? So that means this entire thing is just true. This entire thing is just true, which means you can quite quickly simplify the whole thing to, now if you want to go by alphabetical order, then you want to move the Q ahead of the R because it's PQRS. So it becomes not Q or not R or not S, and not Q or not R or T. So that becomes the C and F, which is the end result. It's one way to get to it. There are many other ways to get to it. You know, if you do a cross product at the wrong point of time, it will still be correct, except you end up with a lot more terms, and then you have to simplify it back to, you know, what we have here.
Where did you get this formula A or B and A or C equals to like?
You mean this thing here?
No, but the one before.
This one?
I mean. Oh no.
This one?
No, never mind.
This one is derived from that one. It's the same thing as what you know in algebra. It's comparable to A plus B the whole thing times C plus D the whole thing. Yep.
We didn't do the distribution on the first part, right? The first part of the expression.
The first
Distribution, before the red marks.
before the red marks.
Yeah, so that expression there before you started.
This is not resolution.
Right above that. Right above that line.
This one?
That line. Yeah, the first part of that term.
This one?
Yeah. Where did you
What did I do with this? I did a cross product. So I look at this whole thing as I look at this whole thing as A, B, C, C, and D, and then I apply this cross product thing to end up with those cross products. Yep.
So the A or B and C, where you got the A or B and A or C, that's just something you memorized from algebra? Or?
It's Boolean algebra. I think that might be mentioned in the notes as one of the steps that you can perform to transform everything to a CNF. Yep.
So if you distributed the left side, it wouldn't have worked? Like
If you
the
distribute
AR?
the left side, it will still work. It's just you end up with something that's longer. So if you distribute the R, not R to this, then you end up with P and not R, or Q and not R, right? But that is still not in CNF. And then you have an OR with the other side. So basically this overall OR, the last OR, is going to end up as a cross product of some kind. So you can do whatever you can with each side, and you can do whatever you want with the other side. But if each side ends up to be some kind of AND, now if it becomes a big gigantic OR, which is what you probably ended up with, then you have to carry out the big gigantic cross product thing. It will still boil down to this, but then you have more simplifications because you end up with a lot more terms. This is just something that I discovered today because I have worked with this last year too. So last year I did exactly what you did, okay? End up with, a whole bunch of blah 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 or blah 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 or blah 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 or blah 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 or blah blah blah. Do one gigantic cross product with everything, and then we started to cross out terms like, nope, this one is useless, that one is useless, that one is useless. Oh, that one is the same thing as that one, and so on. This turns out to be a faster way to get to it. But the other way would still work out. It's just longer. Yep.
I'm a little confused. Alright, so between the red marks, there's the equation, not R, yeah, that one,
Mm-hmm.
and then the one below it that you haven't crossed out.
Mm-hmm.
No, the one below. Yeah, so those two.
Mm-hmm. So those two.
Did you just rewrite them?
Yeah, I just
Or did
rewrote
you-
them because so that it's alphabetically
Oh,
ordered.
okay, so it doesn't, that's what's confusing me. I'm like, why is the Q first?
Yeah, I just rewrote them so that it's alphabetically ordered. The nice thing about alphabetically ordered is when you're doing the resolution, it's easier to spot things that you can resolve, just a little bit marginally faster. So are we good so far? Yep.
If you have time after this, can you talk a little bit about resolution?
Yes, we can talk about resolution. But at this point, are we good so far with all these steps? Okay. But you can actually feel the pain of dealing with open-ended Boolean expressions, because there are so many rules that are applicable at the same time, and it's really hard to see which one is leading you to the goal that you want to get to. Okay? So even if I were to tell you this is the answer, okay, and you only have to write the steps in between, it is still kind of a challenge. It is not as bad of a challenge, but it's still a challenge, because you can take a derivation and it's the wrong direction. It is not wrong, okay? It's just a wrong direction, which means you're gonna go somewhere that is not gonna lead you to the right answer. Eventually, it will circle around to get back to the point that you want, okay? But it will take you a lot longer. And that is the problem of propositional logic in general, is you have a whole bunch of productions or inference rules. They're all valid, okay? As a system, it is both sound and complete. In theory, it can get a job done. But in practice, it is almost impossible to get a job done, because once again, we have an infinite haystack and we don't even know whether the needle is in a haystack or not. Okay, so that becomes a pretty hard problem to solve. And that is why resolution, which I'll get back to, is so nice. Because if you only have, how many variables do we have? P, Q, R, S, T, 5 variables, right? So if you only have 5 variables, the conjunctive normal form can only be as long as 3 to the power of 5, okay? Which is a pretty big number. I have to admit it's not a small number, but nonetheless, it is finite, okay? Now, as long as it's a number that is finite and we can just throw computation power to it, it can be solved, okay? Or at least I can theorize and go like, I think this will take 20 hours to solve, or this will take 20 days to solve. But at least I have a time frame and I know when I'll get the answer, okay? But if I do not use resolution, CNF, and proof by contradiction, because all of those combine to the technique. If I don't use those techniques, then I have no idea. 20 years later, I don't know whether the theorem is just not found yet or whether it's not a theorem. I cannot differentiate between those two cases. Is that okay? All right. Okay, so getting back to resolution, okay. So resolution is one of the 3 ingredients that we need to prove theorems using a computer. So we'll go to propositional logic and go all the way to resolution. I really like the new format of my notes, having a little table of contents, because you can just kind of click on one of those and get to the topic. If you get the PDF, it works the same way. In the PDF, the table of content is actually a list of hyperlinks, so you can actually click and jump all the way to the right topic really quickly. Okay, so this is resolution, and let's not focus on the proof, but only focus on this part. Okay, so we are only focusing on this part here. All right, so what is it saying? It's basically saying, okay, if you find anything that matches this particular pattern. What pattern are we talking about? The overall operation is a conjunction, and then the 2 things that you are ANDing is each one a disjunction. Inside the disjunction, one refers to psi, and the other one refers to the negation of psi. What is psi? Well, for the purpose of this particular proof, psi itself can be a gigantic expression of some kind. I don't even care what it is, okay? But for the purpose of this discussion, it can be anything. But as long as we have psi and not psi on one side and one on the other side, then this implication is going to hold true. In other words, if you can confirm phi or psi, the whole thing, and not psi or rho, the whole thing, if that is true, we know for sure that phi or rho is going to be true. Now, to make it workable using a computer, we place that extra restriction and say that psi has to be a variable only. So that makes it very easy to turn this into an algorithm, because all we're looking for is the appearance of one variable on one side and the negation of the same variable on the other side. That's easy to match. You just need a double loop to do it. Is that okay? So is that explaining resolution? Because that was the earlier question. Somebody asked about that question. Or are there additional questions related to resolution? Resolution is one of the three ingredients that we needed. But it's the mechanical ingredient that we needed. Any questions? Yep.
Is there any other sort of logical formula like resolution that also can simplify a logical expression? Perhaps switch some boards with some hands and negate some variables if you have something else that can also.
There might be other ones that can do it. But the nice thing about resolution is it depends on conjunctive normal form, because once you have the CNF or conjunctive normal form, it becomes easy to spot these things. But conjunctive normal form is really nice too, because any Boolean expression can transform into a CNF. So you can give me any Boolean expression, I would turn it into a CNF. But once we have everything expressed as CNF, then we can apply resolution. So that's the connection between CNF and resolution. CNF is the format that we want things to be in order to apply resolution. But the third piece to this puzzle is proof by contradiction. Because the whole thing about resolution is you start off with three things and you only end up with two, right? So you can kind of see that if we only start off with two things, we can end up with none. Imagine the case where this side, the left-hand side, only has psi, and the right-hand side only has not psi. Then the resolution is resolving psi and not psi to false. Okay? So that means resolution as a mechanism is a way to keep reducing things until you get to false. Well, that doesn't sound very useful because we like things to be true, don't we? What if we prove that something cannot be true? Well, then the opposite has to be true. Something cannot be, okay, so the opposite has to be true. So that's basically the basis of proof by contradiction, which is discussed like down there a little bit. Yeah, where is it? Yep, there we go. Proof by contradiction is discussed down here. So is that okay? I mean, are we getting a handle on what three ingredients are we talking about and why they are all important in the attempt to prove theorems mechanically? Is that okay? All right. Any other questions related to resolution, propositional logic, anything related to the exam, like relations and functions? Yep.
Is resolution and proof by contradiction in the scope of the exam?
I don't think they're in the practice test,
Okay. I just wondered.
right? If it's not in the practice test, we can always leave it to the second exam.
Okay.
It's really just a matter of, what do we want in the first exam, versus the second exam. It's not going to disappear. There's the, huh? So CNF is not going to be in the first exam. Any complaints? Objection? I demand CNF in the first exam because I just learned how to do it. Well, I mean, that's the trade-off, a little bit. If you understand the concept, you might, it might take you a little bit of time to kind of reconnect to the concept. But if you truly understand the concept, you just have to kind of read the notes a little bit or watch the video a little bit, and it will come back to you. Okay, yep?
So are we done with this, all the simplification stuff after this module, or are you come back later?
So, there's no other, okay, when we talk about predicate calculus, then we'll come back to this a little bit, because predicate calculus is, you can look at it as an extension of propositional logic, but at the same time, it can do a lot more compared to propositional logic. So it all kind of, that part depends on whether we have time to get to predicate calculus. I hope we have, because predicate calculus is really interesting. It's really fun. All right. So are we good so far? Any questions about functions, relations, set theory, that sort of thing? Nope. All right. Yep.
Is the grading scale in the syllabus accurate in this class?
Sorry?
The grading scale in the syllabus, is that accurate in this class?
It is. So you're talking about, if you get less than 12.5% of all the scores, you get an F.
Yes.
Yeah. Yep. It's still true. Yep, it's all in the syllabus. Okay, so if you guys want to know what letter grade you are going to get based on what the percentage of score at the end of the semester, you have to read the syllabus. So obviously somebody read and could not believe the syllabus. Did I read this right? Yep, you got it right. All right, so with this out of the way, we're going to continue with lottos, okay? The analysis of your odds of winning in a game of lotto, okay? So we'll go back to the lotto website, okay? So we'll go to, I think it's Super Lotto, right? Huh? Powerball, okay. So we'll go to Powerball Lotto. Wow, that is cool. The first thing that pops up is the winning numbers for this particular week. which basically means enough people are interested in the winning numbers, and that's why it pops up the first time. Okay, so we're going to go to the home page. Okay. Oh, interesting. You can go to one nationwide Powerball website to navigate to the state that we are in. Wow. That's kind of big. Huh? Oh.
And then at the bottom says cash value, 100 something million. Like they take away the taxes.
Yeah, but what they did not factor in is you can have multiple winners. You can actually have duplicate winners, which typically happens when the jackpot is high up. Then you have several people buying the same ticket. So that is the part that is really difficult to account for, is how many people are buying the same winning ticket. And since I don't have a model for that, that's probably a statistical model. If you look at all the past history of purchasing statistics of lotto tickets, you can map the jackpot to the number of tickets actually sold. So with that information available, you can better assess whether it's worth the money to buy your lotto ticket or not. They probably need to disclose that information anyway. Okay, so we're going to play Powerball. And with Powerball, there are 5 numbers or 6 numbers that you have to pick. The first 5 numbers are, okay, so just imagine you have a basket of these balls and they have numbers. I think it's 1 to, how many? Okay, we can read the rules. All right, where are the rules? Number 3, how to play, there we go. And we have to pick, okay, so right here it's specify the rules. Okay, so how to pick, we have to pick 5 lucky numbers. The lucky numbers are from 1 to 69, but once you pick a number, that number cannot be picked again. So in statistics, we call this without replacement. You are choosing something without replacement. So if I choose, if I draw a ball of number 2, I do not put that ball back into the basket to pick the next number. Okay, whatever you pick, you put it aside and it can never be picked again. So that's the first thing. The second one is, so we have to pick 5 lucky numbers, quote unquote lucky numbers, and then you pick one Powerball number from 1 to 26. In other words, the picking of the Powerball is putting everything from 1 to 26 back into the basket, and then you pick one of those 26 numbers. So that means, if you have picked 2 as a lucky number, 2 can again be a Powerball number. So it can reappear, a number can reappear as a Powerball number. Is that okay? And the sequencing is not important. Okay, so that means 5 to, okay, let me just use an easier sequence. 1, 2, 3, 4, 5. Okay, in that order, picking those balls in that number, in that sequence, is really the same thing as 5, 4, 3, 2, 1, which is the same thing as 2, 3, 1, 4, 5, and so on. Ordering is not important. Are we doing okay so far? Okay. So we want to find out, let's just deal with the lucky numbers, okay? How many ways can we pick the 5 lucky numbers from 1 to 69? That's the first question. Okay. So we'll switch to the tablet and then we'll say, how do we analyze this problem? So now you have, imagine in front of you is a basket that has 69 numbers in it, 1 to 69. How many ways can I pick the first ball? 69 ways. Okay, very good. Okay, so we use a tree to represent it. Okay, dot, 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 like that. So the first ball can be 1 all the way up to 69. Okay, that's the first number. What about the second number? That gets a little tricky, doesn't it? Because I can't just universally blanket and say, oh, the second number has to be from here to here. Because it depends on what you chose as your first number. So in the first one, okay, the second number is going to be from 2 to 69 because 1 is already chosen. You cannot choose 1 again. For the second one, 2 cannot be chosen again, so it will be 1, 3, 4, all the way up to 69, and so on. For the last one, 69 is chosen already, so you can only have 1 to 68 to choose from. Okay? So if I were to kind of display that, it's 1 to 68, because 69 is chosen already. So using this analogy, you can kind of imagine the third level is going to be, there are 2 balls or 2 numbers that you cannot choose from. And then at the fourth level, there are 3 numbers that you cannot choose from. And when you pick the last one, which is the 5th ball, there are 4 numbers that you cannot choose from because they have been chosen already. Is that okay? So if I complete this picture, okay, so 2 split, and then this splits again. So 1, 2, 3, 4, and then split one more time, okay? So this is kind of the look of the tree. Is it has how many levels? 1, 2, 3, 4. There are 5 levels to this tree. How many what is the branching or fan out ratio of the first branch? In other words, from here to pick the first ball, how many possibilities do I see? 69, okay? What about the second level? If you pick any node of the first level and say, how many ways can I expand that node? 68, and then 67, 66, and then 65, okay? Okay, so if I want to know exactly how many leaf nodes we're gonna have at the very end, well, that's not too bad. I mean, because it's just a matter of multiplying the number of, or multiplying the fan out ratios per level. 69, okay, so we say it's 69 for the first level, 68 for the second level, 67, 66, and then 65. Multiply these numbers together, and what do we get? You get the total number of ways to choose 5 balls, but you are counting 1, 2, 3, 4, 5 as a different thing from 5, 4, 3, 2, 1. Is that making any sense? Because, you know, within the first level, I choose 1 here, okay? But I can choose 5 over here. 2, 3, 4, 5 ends up here, and then 5, 4, 3, 2, 1 ends up here. They are different entries. Is that okay? Yep.
So hopefully this isn't a stupid question, but
There are no stupid questions,
okay. So you did the,
but there are stupid answers. I can give you one.
how did you know intuitively just to use multiplication? Like I knew it was multiplication.
It's multiplication because, okay, so this is something that we have heard before, but the significance is different in this lecture, because for each node of the first level, it branches out to 68 different things. Now, so if the first one has 68, the second one has 68, and we have 69 of those things, so you end up with 69 times 68 second level nodes. And then we say again, for each node of the second level, it branches out to 67 things. That's why we use multiplication, because of the word for each. But this is a different context. It's not exactly, well, it is used as a universal quantifier, but it's used to explain why we use multiplication. Is that okay? All right. So we multiply all of these numbers, and it comes up to a pretty big number. It's actually bigger than the odds, you know, in the lotto game, because this is giving us the number of permutations. Now permutation, oops, okay, running into the quick button thing. Permutations. Okay, so permutation as a word is derived from mutation, and that has to do with ordering. Okay, and that's why you have the commutative, you know, law of, you know, addition and multiplication, where, you know, the ordering is not important. But when you talk about permutation, the ordering is important. 1, 2, 3, 4, 5 is considered different from 5, 4, 3, 2, 1. Is that okay? But the lotto game sets, it really doesn't matter how the 5 numbers are chosen. Okay, you can choose like 5 and then 1 and then 2 and then 3 and then 4. It's still considered the same thing. So now how do we shrink the number of permutations down to, you know, okay, we just need to know which 5 numbers. The order is not important. How do we shrink it? So the way to think about this is to look at a new page, okay, and then we say, okay, so let's say we are only interested in A, B, C, D, E. So these are chosen already, okay? How many ways can I order these? How many ways can I reorder these things so they look different? That becomes the next question, okay? You got 5 things. We just want to shuffle these 5 things so they look different, so the ordering is different. Well, don't you think we have seen this problem before? What can I choose as the first of the 5 things? There are 5 ways to do it, right? I can choose A as the first, I can choose B as the first, I can choose C as the first, I can choose D as the first, or I can choose E as the first, right? Okay, let's say I chose 1 as the first. What choices do I have after I have chosen A as the first? Now I'm choosing the second one. I got 4 choices, right? Yep, exactly. We got B, C, D, E as my second choice. Let's not always just pick the first one. This time let's pick D, okay? I have chosen A, I have chosen D. I got 3 more things I can choose at this point. What 3 things can I choose? B, C, and E, okay? So I got B, C, and E. And let's just pick on C at this point, okay? What 2 things have not been chosen on this particular path? B has not been chosen, E has not been chosen. Let's pick E in this case. Well, do we really have a choice? Nope. Okay. So once again, we are looking at a tree. I'm only looking at a very small partial part of a tree here, okay? But the bottom line is, how many choices do I have at the first level? I got 5 choices, okay? For each node of the first level of the tree, how many choices do I have for the second level? 4. And then for each node of the second level, how many choices do I have for the third level? 3, 2, and then down to 1. So what do we get? Yep, we got 5 times 4 times 3 times 2 times 1. This is the number of permutations of choosing 5 out of 5 things. Okay? Okay, so how does this connect with the previous thing? The previous thing, let me go back to the previous slide. The previous thing, says we got this huge number, which is 69 times 68 times 67 times 66 times 65. That's the number of permutations of choosing what again? Okay, let's be more specific now. Of choosing, we're choosing the lucky numbers of Powerball Lotto. So how many things are we choosing? We need 5, okay? It's choosing 5 out of how many again? 69, sorry. Okay. Okay, so how are these things connected? I see the 5, connecting between this slide and the next. So how are they exactly connected? This is telling me that there are this many ways, okay? If you multiply these 5 numbers, that tells me the number of ways of choosing 5 things out of 69. And the ordering is important, okay? 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, 2, 3, 4, 5, 1. They're all considered different. And then the next slide says, if we just look at 1, 2, 3, 4, 5, okay? There are 5 times 4 times 3 times 2 times 1 many ways to shuffle the ordering so they look different in the first slide. So if I just need to know how many ways can I choose 5 numbers out of 69, ordering not being important, what do I need to do? Divide it, exactly. So we divide 69 times 68 times 67 times 66 times 65 by 5 times 4 times 3 times 2 times 1. That gives me the number of ways of choosing where ordering is not important. Because I'm looking at 1, 2, 3, 4, 5 and go like, okay, how many ways can we organize 1, 2, 3, 4, 5? We got this many ways, okay, which by the way is 120 ways. Yep, go ahead. It is not a summation. Okay, so if I look at this, then so the math that we're looking at is 69 times 68 times 67 times 66 times 65 over 5 times 4 times 3 times 2 times 1. The numerator tells me how many ways I can choose 5 out of 68 items, ordering being significant. Okay? The bottom one, or the denominator, tells me given 5 things, okay, I've already chosen, this is the 5 balls, the 5 numbers that we are interested in. How many ways can we shuffle those 5 things so they appear different in the first part of in the numerator? So when you divide these two, then we get the number of ways of choosing 5 things out of 69, where ordering is not significant anymore. Okay? Now, working with huge numbers like this, sometimes you cannot really see what's going on, so we shrink the numbers. Okay? So we look at something that's manageable. Let's say we are looking at how to choose 2 out of 4 things where ordering is not important. Is that okay? Because that we can actually enumerate, physically. So choosing 2 out of 4. So we'll go ahead and just write it down here. Okay, choose 2 out of 4. Okay. Out of. Transposing in my head. Okay. So the first one we can have A. Let's see how many. Okay, just A. 3 of those. Okay. We got B, C, and D. And then at the second level, we can have B, C, D, and then we have A, C, D, and then we have A, B, D, and then we have A, B, C. Okay, so do we agree that this is all the ways we can choose 2 out of 4 things? The 4 things being A, B, C, D. Okay? If I pick any 2 items, okay, let's just randomly pick A and C, okay? How many ways can we arrange A and C? So we got AC in this particular order. We got CA in this particular order. Right? So if I ask you, how many ways can I pick just 2 things out of A, B, C, D, but ordering is not important, then you cannot count these 2 as separate ones, right? So now we pair up things and go like, okay, these are duplicates. Count them as 1, okay? Count these 2 as 1. Count BA and AB as 1, okay? So these 2 are 1. AD and DA counted as 1. Let's see, BC and CB is 1, BD and DB is 1, and then CD and DC is 1. There we go. Okay, so we are counting 1, 2, 3. Okay, this is not a very systematic way to do it. 4, 5, and there should be 6 of them. So where's the 6th one? Oh, okay. Okay, so we got the 6th. Okay. Not very systematic, but visual. We got 6 of them. Okay, so does the math work out the same way as the other one? Think about 4 times 3 times 2 times 1. That's the number of ways of choosing. Take it back. 4 times 3, okay? 4 times 3 is the way, the number of ways of choosing 2 things out of 4 where ordering is significant. Given any 2 things, okay, you get 2 times 1 ways to shuffle the orders. So they appear distinct, okay? So when you do the division, 4 times 3 is 12, divided by 2 times 1, which is 2, that's 6. So it is actually 6. We can have 6 ways of choosing 2 out of 4 items. It is also known as 4 choose 2 because we are counting the combinations. So these 2 words are very, very important. Combination means the ordering is not important. Okay? We just need to know the membership. So relate combination to the concept of a set versus permutation, where the ordering is important. relate permutations to tuples. Is that okay? All right. So getting back to our example, okay, let's work out that number. So the best way to work out numbers is to use a spreadsheet. So I just randomly pick a spreadsheet. And no, that one is not good to use. Okay, we'll start a new one. All right. So we'll start with a few numbers, okay? So this is going to be the number of permutations choosing 5 out of 69. And this is going to be the number of permutations choosing 5 out of 5. And they will plug in the numbers that we have already computed. So this is just 69 times 68 times 67 times 66 times 65, which is a pretty big number. And then the next one is 5 equals 5 times 4 times 3 times 2 times 1, which is 120. And then now we say, what is the number of combinations? So we'll use the correct term here. 69 choose 5. And that's just a division between these two numbers. Okay, divided by that. Okay. So this number is the number of combinations as far as the lucky numbers are concerned. But remember, to win the jackpot, you also have to match the Powerball number. I think the Powerball goes from what, 1 to 26? Okay, so that means I have to multiply this number by 26. So this number times 26. This number should give us the odd of winning. In other words, your odd of winning is 1 divided by this number. Okay, so let's double check, right? Just in case my math is off. So we go back to the browser. Oops, we are already in the browser, just different page. So we go back to here. By law, they have to disclose the odds of winning. So I think is it? Nope, it's not number frequency. It's the something else. FAQs, no. I know by law they have to disclose the odds of winning. There we go, odds. Well, is that number matching what we have? Okay, so it ends with 338. And our spreadsheet is ending with 338 as well. So it is exact. So the next time you have a question in your head like, why do I have to take cisp440? That seems like a math class. It's totally useless in programming. Well, at least it will convince you when and when not to buy a lottery ticket. If not for anything else, okay, this is helpful. I'll see you guys on Thursday. Don't forget Thursday is exam 1. It is open book, open notes. Wednesday, sorry, thank you, Wednesday. The next class meeting.